All right, we're going to continue developing data structures in Java. And in our last class, we made a linked list by hand. We created the building blocks of a linked list. We're going to do the same thing this class for a binary tree, not because necessarily this is something we're going to need to do often, but as an example of building up a data structure. And we're going to see something similar to what happened with the linked list. We're going to actually create a pair of classes, one for the nodes of the tree, and then one for the tree itself, which is made up of those nodes. And the interesting thing here is that, again, like with the linked lists, all of the sort of heavy lifting is going to happen in the node class. And the tree class is going to be mostly wrappers around the nodes. So I'm in a work area here. Let's make a tree node class. So this will be main class for a single node of a binary search tree. And so what do we need in here? Let's make an integer data, and then let's make a tree node left, and then a tree node right, and those will be the children. And that may be all we need for our tree node class, but we're going to add some additional methods in here. So let's make a constructor. Let's make a constructor that creates a tree node with a given data value. So we'll make this public tree node integer d. And we'll just create a new node. We'll set its data value equal to d, and we'll set left and right equal to null. Now, I'd like to introduce something else at this point. When we make a constructor like this, we have to name the argument. I'm calling the argument d, and then setting data equal to d. Why d? Because d stands for data, right? But I keep saying that we should use good variable names. So ideally, we'd like to call the argument to this tree node constructor data. But if we do that, our statement to assign the data value becomes data equals data, and this is silly, right? Saying data equals data does nothing. And the problem here is that, once we have an argument to the function named data, anytime we say data, it means this argument. So yeah, this thing on the right-hand side of the assignment, that's the argument to the constructor, but it's not storing it up here, it's storing it in a local variable named data, which is the argument, which is why this is a no-op. So saying data equals data doesn't really work. What we really want to do here is take this argument, data, that's the right-hand side of the assignment, and we want to copy it into this data up here. Right? The data that is part of the class, not the data that's a local argument. So we'd like to say, hey, I'm talking about the field named data in this current class. And there's a way to do that. And the way we do that is with the keyword this. So when we say this dot data, it means, okay, this is the current object, right? The thing that we're constructing in this case. Go into that object, look for a field named data. That's going to pick up this thing right here. So this keyword this is one of the places it gets used most is in constructors, so that we can have the same name in this argument as we have for a field, but this dot data refers to the field named data in the class itself. Data by itself refers to the most locally scoped or declared version of data, which in this case is a local variable because it's an argument. So this dot data means this thing up here. So this takes the argument to the constructor, stores it in the data field. Left and right, we don't have to say this because there's no variable in here called left or right. Now if I declared something inside here and I named it left, then I would have to say this dot left if I meant you know, the field in the object named left. So, but for data, we're using the keyword this to say data up here as opposed to data down here. All right, so there's a constructor, and let's make an add method. So let's add a node to the tree, and the idea is if we have the root of a tree, right, which is a tree node, we want to be able to call the add method of that node and have it update the tree to add a new node containing a given data value. But what we're passing to this is the root of that tree that we're trying to update. So let's write some code, and now let's talk about what exactly it does. So this is going to be public void add integer data. And we don't have to worry about the case where our node is null, because this does not work if we don't have any nodes, right? This is assuming that we already have a root of a tree. It's not null, we have a root, and we're saying, hey, you know, the tree that's rooted here, I want to add a new node to it. So all we have to do is add to either the left subtree or the right subtree. All right, so let me put a comment here. So add to either the left or right subnode of the current tree. So if data is less than, again, this dot data, so compare new data to the root. And let's see if it should go to the left. All right, if we decide that the new data should go to the left of the root, but the current left child of the root is null, make a new node as the left child. So if that's the case, we're going to make a new tree node. We're going to set left equal to that, and we're going to return. All right, so what's going on here? We compare our data to the root data. If it's smaller, we check to see if there's anything on the left. If there's not, we create a new node with our new data, and we make that the left child of the current node. Otherwise, there's something to the left, and so we're going to go ahead and add to the left subtree, which is just left.add data. In other words, left is the left subtree, or the root of the subtree on the left, and that comes with an add method. And so let's call that add method and add the data that we want to add to the tree. And that's all there is to adding on the left. So if our number is smaller than the data, either there's nothing to the left of the root, so we're going to make a new node and make that the left child of the root, or there is something to the left, and so we're going to call that node's add method and add to that left subtree. So here we should add to the right. So let me rip off some of this code. So if right is null, then make a new node as the right child, and we'll just set right equal to new tree node and return. Otherwise, we add to the right subtree by just calling right.add. And that's the end of the add method. All right, Let's make a method for traversing the tree in order. So we'll call this LNR for left node right. Doesn't need any arguments. And all we've got to do is the following. So if left is not equal to null, let's just traverse the left subtree. How do we do that? By calling the LNR method on the left subtree. And then let's print out data plus a space. And then let's traverse the right subtree if right's not null. And that's our traverse method. All right, so that's a tree node class. Let's compile that. And now let's make a main program. So I'll just call it main. And let's initialize a tree node containing 10. And then let's add some data. And then let's traverse our tree finally. Alright, so we'll compile that and we'll run it. And there's our data. 5, 7, 10, 17, 20, 30. Those are the values that we added, and since we're traversing in order, they're coming out, you know, in increasing order. Alright, we'll take care of the fact that there's no new line at the end in a minute. Because, you know, while this works great the way we've used it, this is not exactly how we want to set up our binary tree class. And the difference here is that, you know, to create my tree, I had to first create something with a root node, right? And usually when we write a program, we like to begin with a tree that's empty and then add things to it. And similarly, if I had a delete method and I deleted the last node from the tree, I would need my root to change from what it is now to being null, right? And if I require a non-null tree node in order to do things like add to the tree, I have a hard time getting this started, right? If my root is null, I can't call root.add to add the first node, right? The structure of my tree node class is forcing me to have at least one node before I can do anything like add more nodes. And it doesn't get us from the case of the empty tree to a tree containing one node. So here's what I'd really like to do. I'd really like to say my tree, root equals new my tree. And then I'd like to be able to call root.add and add some things to it, and root.lnr to print things out. But I really want to begin with an empty tree. So we're going to make a new class. It's going to be called myTree, and it's going to be built around the tree node. So let's make myTree.java. So this is mostly a wrapper. Around the tree node class. So inside here, I'm going to keep a root. So tree node root. And in my main program, instead of calling my tree a root, I'm going to call it tree. Because, you know, when I initialize this, if I call this root, but it's really null, it's confusing. It's not really a root node, it's really a tree, right? So tree is a new my tree, and then I can say, to this tree, let's add something. With this tree, let's traverse in order, and so on. So the root is going to be part of the my tree class. It's going to keep it as a tree node, and it's just going to be null. So we start with an empty tree. And we're not going to need a separate constructor for this, because we don't really need to initialize anything. I'm setting up the root to be null right here. But let's make our add method. So we want to add a piece of data to our tree. So add a new node with a given data. And here we're going to deal with the edge case, right? If root equals null. So if the tree is empty right now, then we'll just set root equal to new tree node data and return. And if the root is not null, the root is a tree node, right? And tree nodes have an add method. So how do we add to the tree? We just say root.add data. And we're done. Let's do our in-order tree traversal. So this is public void left node right. So if the root is equal to null, then there's really nothing to do, right? We can just say return. Otherwise, we can call the traverse algorithm in the root. And then here, we can go ahead and print out that new line at the end. And that's our LNR method. So we can compile our main program, run our main program, and it does exactly the same thing, except, you know, we've also got the nice new line at the end. But what's happening here is we've created a tree which will exist as soon as we call the constructor. It's not null, but a non-null my tree can still represent an empty tree. So in the beginning here, I can say something like let's call LNR on the empty tree and say root.lnr. And then down here, let's call LNR on the full tree and print that out. That should be tree. Semicolon. Alright, so compile that. Ooh. Little typos. Compile that. Run our main program. So on the empty tree, you can see LNR didn't print anything, but it doesn't have any difficulty either, right? Because the my tree exists, right? And inside my tree, root is null, right? But that's okay. The code inside the my tree class will say, hey, if you're trying to print out the tree and the root's null, just don't print anything. So we get the correct behavior. All right, so that's basically all there is to an implementation of a binary search tree, and it has this similar structure where, you know, the tree class doesn't really do a whole lot of work, and the real work is happening inside the node class. And if we wanted to write a delete method or a search method or, you know, a rebalance method, that would all happen inside the node class, and the tree class would just be wrappers around that. All right, so next class we're going to talk about generics, and we'll make our tree class generic so it works with things other than integers, and then we'll talk about class extensions.